Good morning, Year 12s. Sorry I can't be in school today, but we're going to try and have as normal a lesson as possible. So today's lesson is going to be on wave-particle duality, which is the final topic in the Year 12 Particles and Quantum section. We'll finish it properly when I'm back in school tomorrow or next week, but we'll do the vast majority of it today. As usual, we'll start with a quick recap of what we did last week, and then we'll move on to the new topic. So last week, we were looking at absorption and emission spectra. So what I'd like you to do now is to pause the video and tell the person next to you as much as you remember about this topic. And I would suggest you spend about 2 minutes doing this. So pause the video now and discuss this topic. Okay, so hopefully you got all the key points. So in this diagram here, we can see two pictures. The top one is an absorption spectra, and it happens to be for hydrogen. The bottom one is an emission spectra for hydrogen. So the emission spectra is caused when electrons move down energy levels and emit photons. And the absorption spectrum is caused when photons move up energy levels and absorb photons. And hopefully you mentioned that every single element has its own emission spectra and also therefore corresponding absorption spectra, and they're a bit like a fingerprint for each element. If you are investigating a mystery element and you shine light at it and you then measure the light that it gives off, and you do this for helium, helium will give off these wavelengths of light, and only these wavelengths of light, and no other element will give off these same wavelengths of light, so you can tell that it's helium. And this is really, really useful if you're investigating what gases are in a star, for example, or what gases are in a planet in another solar system, or even what makes up the tails of asteroids. If you can examine the light that comes off it, you can work out exactly what elements it's made of without ever having to go there. And this is obviously also useful in chemistry if you are trying to identify an unknown compound. If you have previously worked out the emission spectra for that compound, and you can identify it even if you don't know what it is. A little bit more information about how they're produced. So you can see in this diagram here, we have a bulb in the center. So this bulb is going to be giving off white light. And we can tell that because if we look at the bottom here, if we split that light up through a prism, you can see it gives off all the colours of the rainbow. So we know it's the full white light. You might be wondering why this slit is here. Well, you know why the slit is here from your waves lessons. And that is, of course, to make sure that this light that goes through is obviously a narrow slit, but it's also therefore coherent light. And we know that that's important. Because it allows us to get these diffraction patterns really nicely, and that won't happen if the light isn't coherent. So how do we get absorption spectrums? Well, we shine this white light through a cool gas, and that gas will absorb its characteristic frequencies, and therefore it will leave behind the rest of the wavelengths of light, which will make up all the other ones to make white. If we shine light at this cool gas and we just let this cool gas re-emit those photons on its own, then that cool gas will only give off its characteristic frequency, so it will give off its emission spectra, so it will be a lot fewer lines. You might be wondering why the absorption spectrum isn't also going to give off these lines from the emission spectrum. Well, that's mainly because all this white light is going through it, and it kind of drowns out these lines here because the intensity of the white light is just so much higher than the emission spectrum of the cool gas. It's not the full explanation, but I think that's good enough. And the last thing that we looked at last week was one specific example for hydrogen. So in hydrogen, if we look at the emission spectrum, because we understand hydrogen so well, because it's a very simple atom, we know, or actually we've given names to the different parts of the spectrum. So there's kind of three specific names that you'll see and you'll need to be aware of for your exams. The Lyman series, the Balmer series, and the Passion series. And what these are is different sets of transitions. So the Lyman series is transitions from the second, third, fourth, fifth, and sixth energy levels down to the ground state. The Balmer series is looking at the emissions from the third, fourth, fifth, and sixth down to the second energy level, and the Passion series, the next one up. So what do these correspond to? Well, the Lyman series, because these are quite large transitions, corresponds to ultraviolet light. The Balmer series, slightly lower, so this corresponds to visible. The Passion, again, lower energy still, so it's the infrared series. And then there are more, far infrared and even further infrared, but we don't need to know these for A-level. We just need to know these three. There really isn't that much more to say about these. Typical questions will be like, work out the energy that this first one corresponds to, or work out the wavelength of light or the frequency of light. And you know how to do that because we've done those kind of questions many times. So I'm going to give you a few questions now. So the first few are going to be multiple choice questions. So this first question, this diagram shows some energy levels for a hydrogen atom. An excited hydrogen atom can emit photons at certain discrete frequencies. Three possible transitions are shown in the diagram, A, B, and C. The transitions shown in the diagram result in photons being emitted in the ultraviolet, visible, and infrared regions of the electromagnetic spectrum. Which of the regions do A, B, and C correspond? So is A, ultraviolet, visible, or infrared? Is B, ultraviolet, visible, or infrared? Pause the video now and spend 30 seconds discussing the answer. So this is a relatively easy question. The largest energy gap must be ultraviolet, so that is C. The smallest energy gap must be infrared, so that is A. And then B is the one in the middle, that is visible light. Question 2. This diagram shows an energy level diagram for a hydrogen atom. Electrons, each having kinetic energy 2.0 times 10 to the minus 18 joules, collide with atoms of hydrogen in their ground state. Photons are emitted when the atoms de-excite. How many different wavelengths can be observed with incident electrons of this energy? 1, 3, 6, or 7. Pause the video now and spend some time, spend about a minute on this question. Okay, so in order to answer this question, you first need to work out the energy of the electrons in electron volts. So you need to convert this to electron volts. And you then need to decide where that means you can get to on this energy level diagram. Now, because I'm just going to pause the video now and work out the answer. Okay, I really should have found my calculator before this recording. So when you type it into your calculator, the conversion, you get 12.4 electron volts. So that means that the electrons can go up to this energy level here. So how many ways can they de-excite? Well, they could go all the way back down for 1. That's not the correct answer because they could also go down to this energy level and then down to this energy level. So the correct answer is 3. Okay, question 3. The diagram shows the 4 lowest energy levels for an electron in the atom. P, Q, R, and S represent to scale the relative energy values of these energy levels. An electron transition from level R to level Q is accompanied by the emission of a photon of visible light, which electron transition will be accompanied by the emission of a photon of infrared radiation. Relatively easy question. Give yourself 30 seconds for this question. So R to Q is visible light, so we need an energy gap with a smaller difference, so that is going to be S to R, so that's going to be A. Final multiple choice question. The diagram gives some of the energy levels of a hydrogen atom, and it's not to scale, importantly, but they've given you the numbers, so it doesn't matter. The transition of an excited hydrogen atom from E3 to E1 causes a photon of visible light to be emitted, which transition causes a photon of ultraviolet light to be emitted. So again, a relatively simple question. Give yourself 30 seconds to work out the answer. So of course we need an energy gap that is bigger than E3 to E1. So if we go down all of these options, the answer that will do that is E1 to E0. So this is D. Okay, slightly longer question now. The diagram below shows the line spectrum of a gas. Explain how the line spectra are produced. In your answer, you should describe how the collisions of charged particles, this is important, it's not talking about photons, it's talking about charged particles with gas atoms can cause the atoms to emit photons. And secondly, how spectral lines are explained by the concept of discrete energy levels. So 6 marks, so you need at least 6 bullet points. So you should pause the video and give yourself 6 minutes for this question. So the answers, or the points that you should have in your answer, are all of these points on the board. Well, actually, you probably need 6 of them in reality, not every single point. Make sure you note this point at the bottom, although, of course, all of you will have mentioned photons. Pause the video now and spend a couple of minutes marking this. Okay, so let's move on to today's lesson. So today's lesson is all about wave-particle duality. So this is the really exciting, really weird bit of physics, and we're going to explain that today. So you know from your waves lessons all about diffraction, and you know that waves will diffract or spread out as they pass through a gap or around an obstacle. You know, if you have a wave going around the top here, it will also diffract. But usually we see it through an obstacle. And we can see here that the smaller gap means more diffraction, more spreading out. And you should, of course, be able to tell me that maximum diffraction happens when the size of that gap is equal to the wavelength. So this is a much bigger gap than the wavelength, so we only have a small amount of diffraction. This is closer to the wavelength, therefore it's more diffraction, but it's obviously not exactly the same as the wavelength, so it's still not maximum diffraction. If we made this gap a bit smaller, we'd have even more spreading out. So this is going to be really, really important for later on this concept. And this is probably one of the key concepts underpinning this lesson. It's also really nice to see how different areas of physics are starting to link together. So another question for you. How can electromagnetic radiation behave both like a wave and like a particle? Now, there are 2 bits of evidence for particle and 4 or 5 bits of evidence for a wave. So what you need to do is make 2 tables in your a table in your notes with 2 columns: evidence for wave, like nature of light, and evidence for particle, like nature of light. And then you should fill out those columns with the different pieces of evidence. So pause the video now and spend 2 or 3 minutes filling out that table. So what are the bits of evidence? Well, we have these bits of evidence for it being a wave. All waves diffract, all waves interfere, all waves reflect and refract. I mean, they may produce 2 separate points. And all waves are polarizable as well. So not all waves. Transverse waves can be polarized. Longitudinal waves can't be polarized. But if it is polarized, it must be a wave, because particles wouldn't be polarized. You might have put dispersion as well. Now, dispersion is really refraction. So it's not wrong, but refraction is the better answer here. Evidence for particle nature, the photoelectric effect, and also line spectra. as well. Okay, why is this for the particle nature? That's because line spectra are quantized. They are definite energy levels. And we know that only photons of the exact energy between two energy levels can be absorbed or will be emitted. We don't find, electrons being promoted an energy level after waves have been absorbed over a period of time. Just like in the photoelectric effect, it's the instantaneous emission of electrons. It's not something that happens over a period of time when waves just continually get absorbed. So make sure you are very, very confident being able to quote and explain all of these pieces of evidence. So we're going to look a bit more at interference. So again, this is a recap of things you've done in waves. This is nothing new. You would have seen these diagrams in your waves lesson, and you probably would have joined up the points where all of the peaks meet and the points where the peaks meet the troughs. And you'll have looked at the points where you've got constructive interference and destructive interference. So you'll know that if you have two sources of waves, whether it's water waves or whether it's light waves, you get this pattern on a screen, or you get this pattern further along, where you have constructive interference and destructive interference. You get these bright fringes and you get these dark fringes. Okay, like I said earlier, it's important they're coherent, so they have a similar frequency and wavelength and a constant phase difference. And sometimes that's achieved by putting a single slit before the double slit. So here, this is just a representation. This could be water waves, so we don't need that single slit. But if it was light, we would probably have a single slit before a double slit. So we know that waves will interfere and create patterns like this. And obviously from your wave lessons, you know how to change the spacing of these fringes, and you know what other effects will be caused by changing wavelength, the change in distance to the screen, etc. We're not going to worry too much about that now, but it's just important this basic concept is there. So this is the sort of experiment. You shine laser light at the double slit and you get this pattern here. And if you haven't already done this in your wave lessons, you will be doing this experiment. Now, what happens if instead of shining light, we shine particles at the double slits? Well, this is where it gets really, really interesting. So if you just had one slit and you were shining or firing particles through a single slit, so imagine this slit here is covered up. We just had a single slit. The particles would move through and the particles would hit the screen, and they'd basically all hit it in the same place, okay? Because we've just got a gap, and particles don't really do anything when they go through the gap. But what is super interesting is when you have two slits and you start to fire particles through, such as electrons, you get a pattern. Actually, you wouldn't get exactly that pattern for these two slits. You would get this same pattern here. So if you fire electrons through these slits, you actually get this pattern here. If you cover up one slit, you don't get this pattern. If you put a little detector by the slit so that you can, in theory, measure which slit the particle goes through, this pattern disappears. However, if you just have two slits and you fire the particles, you get this pattern, which is really weird and really counterintuitive, and was a really big revelation in physics. So why is that happening? Now, like I said, this pattern you wouldn't actually get with double slits, but you'll see this pattern again in a second. Okay, because this is the characteristic pattern for electrons. So what we're seeing is electron diffraction or particle diffraction, but we're going to focus in on electron diffraction. And that is the weird phenomenon that electrons, if you do this experiment, diffract. They behave like waves. So even though we've thought of them as particles for many, many years, actually sometimes they behave like waves. So it's at this point in the lesson, usually I get loads of questions, and I hope that you're bursting to ask me this question, which is, so are they particles or are they waves? What's the answer? Well, this is where it does start to, really like blow my mind, and hopefully sort of will really make you think as well. They're both. They are both waves and both particles, and it purely depends on what experiment you do. We do experiments, we get evidence, and we try to build a conclusion based on that evidence. So if we do this experiment, we get evidence that suggests they're waves. If we do different experiments, we get evidence that suggests they're particles. Sometimes in science, one of these experiments might be proven to be wrong, and therefore we can discount it. But for electrons, they are both particles and both waves. Now, we'll talk more about this next week. You can ask me as many questions as you want next week if this isn't clear. But for now, you just have to accept that certain experiments show one type of property and certain experiments show a different type of property. So we're looking at the wave property. So one thing you're not missing out on with me being absent is a demo, because we actually don't have this equipment in school. So this is the exact same video I would have shown you at school anyway. So I'm going to play it now so you can actually see this piece of equipment being used and see it being explained, because knowledge of this equipment is quite important.
This is an electron diffraction tube. It's a standard piece of equipment that we can use to show the wave behaviour of electrons. Now, it's not used as widely as it might be, but let me show you how safe and straightforward it can be to use. This bit here is an evacuated bulb, and the biggest risk of using this equipment is probably that you might break this if you don't handle it with enough care. At this end, we've got an electron gun, a heated filament which releases electrons, which are attracted to the anode here, where they pass through a small hole and create a narrow beam, which travels across the tube and strikes the fluorescent screen here. Now in this tube we've got a thin sheet of graphite here in the path of the electrons, and it's this which causes the electrons to be diffracted. Now in order to use this, we need an extra high tension or EHC voltage supply. This is the power supply I use. It's got a high voltage supply here for the anode and a separate low voltage supply here for the cathode. We're essentially connecting two circuits. Now the reason why it's safe is that there's a high value resistor in series with the high voltage supply here, so the maximum current you can get out of it is not really big enough to do you any harm. Now before doing anything else, I make sure that all the switches are set to off and the voltage controls are set to 0. I then connect the 0 of the high voltage supply to the earth and the 0 of the low voltage supply to the same earth. Next, I connect the outputs of the low voltage supply to a couple of wires, so I'm ready to connect the cathode. And next, I'll plug in the anode, for which I use these shrouded connectors, and that's so that there aren't any exposed bits of metal at high voltage. So that's the thing wired up and it's ready to turn on now. And I'm going to start by switching on the cathode, which takes a little while to warm up, but there you go, you can see it starting to glow now, which means you can turn on the high voltage supply. And I'm going to turn that up to about 3000 volts. Now what I hope you can see is a green dot surrounded by fainter concentric green circles, and that's a diffraction pattern that's produced as the electrons fly through the graphite. Now you can increase the energy of the electrons by increasing the voltage. You can see that's changed the diffraction pattern. The rings are closer together, and that's because at increased energies the electrons have a shorter wavelength and they're diffracted less by the graphite. There's one more thing you might want to do with this apparatus, and that's to convince your students that the pattern is genuinely produced by electrons, that is charged particles, and not by a beam of light. And to do that, you use a magnet. And if you bring that close to the beam, you can see that it deflects the image on the screen. And that certainly wouldn't be happening if it was being produced by a beam of light. Now, once you're done with the apparatus, obviously you turn it off, but it's best to wait a few minutes before disconnecting, because it can take a while for the high voltage to die down to zero.
So this piece of equipment is something you'll see a lot in exam questions. It looks a lot more complicated than it actually is. We can go through it again when I'm back in school in more detail, but it's basically a cathode that you heat up. Electrons are emitted. They travel through a piece of graphite, and then they hit a fluorescent screen. This is a vacuum. It should be fairly obvious why it's a vacuum. You don't want the electrons to interfere with any air. And you also saw this green pattern. Now, obviously, electrons aren't green, but you should have noticed that he mentioned a fluorescent screen, and you know how fluorescence works because we talked about it last week. We talked about how the fluorescent lights in the classroom work, and this is exactly the same process. Electrons hit the screen, and they go through the same process that we described last week. So what are some of the key points you need from this experiment? So you need to know that electrons act like both particles and waves. I'd suggest you make a note of all of these points as I go through it. And very interestingly, at the end, he got a magnet and he showed you that in the same experiment, you can get two pieces of evidence that they're particles because they are deflected by the magnetic field, but also they're waves because they're diffracting in the same path, which is just completely bonkers. They are both waves and particles at the same time. Secondly, this is what I've just said. Thirdly, electron diffraction tubes fire electrons through graphite. That's the material. And the reason that graphite is chosen is because graphite has the same or very similar atomic spacing to the wavelength of the electrons, which means you get maximum diffraction or close to maximum diffraction. And he told you what would happen if you increase the voltage, it increased the energy of the electrons, and therefore decreased the amount of diffraction that was going on, because you're obviously changing the wavelength of the electrons. The reason it's circular is because graphite's a 2D surface, it's not just two slits, and this is what I've just said. So I'll give you a few seconds now to copy these down. Okay, so how can we work out the wavelength of electrons, and how does that relate to something that we can calculate? So this is where this equation that we briefly saw last week in the homework and I told you to ignore comes in. So it's known as the de Broglie equation. I know it's spelled de Broglie, but it's usually pronounced de Broglie. So Louis de Broglie was a scientist or physicist in 1924, and he figured out this relationship between a particle's momentum and its wavelength. So wavelength is obviously a wave property. Momentum is a particle property. And he figured out that it was this relationship. So wavelength equals Planck's constant over momentum. This is given to you on your formula sheet, but as with many equations, it's worthwhile remembering this. So we're going to briefly show you how he got to this equation. So it's worth writing this down. So he started with two equations, the relationship between the energy of a photon and its wavelength. And he also started with E equals mc squared. So the fact that energy and mass can be converted. C is obviously the speed of light. So he combined those two equations, and some of you may already have noticed how this is going to work in your head. We combine them. C, the speed of light, cancels. And we rearrange then for wavelength. So we get this relationship. Wavelength is Planck's constant over m times the speed of light. And this step here, you might not be super comfortable with, but just for now, play along. Okay. If it's not light, we're going to replace the speed of light with the speed of a particle to get a more general relationship for anything that is not a photon. So we end up with this. Wavelength is Planck's constant over mv, or lambda is h over p, because p is momentum and mv is momentum. Now, this is not really the proper derivation. It's a little bit kind of loose, but step 3 here is a bit cheeky, right? We shouldn't really be able to do this without further explanation. So please bear in mind, this is not the full rigorous derivation, but it's a way that you can sort of understand that this is not completely made up. There is some physics behind it, and this is not, a million miles away from the true derivation. There are 3 questions for you to do. So pause the video now and give yourself 3 or 4 minutes to do these questions. So the answers are on this slide here. And importantly, the little bit at the end here is worth reading and taking on board. Okay, because obviously, if I run down the corridor, you don't think of me as a wave, and you shouldn't think of me as a wave, because that wouldn't actually mean anything, and it wouldn't be meaningful in physics. But when we talk in terms of particles like electrons or protons or quarks or mesons or whatever, the wavelength is a lot more meaningful. Now, 6.6 times 10 to the minus 10 meters. You could convert that into nanometers, for example, so that'd be 0.66 nanometers, and then you could realize that's going to be sort of ultraviolet to X-rays. Now, obviously, I'm not saying that this electrons become an X-ray or become ultraviolet, but at least you can compare it to something that you know from the electromagnetic spectrum, and you can see it is a bit more meaningful than this wavelength here, which is just ridiculously small and would be like far, far into the gamma region. And obviously, I'm not a gamma ray. And then in, the last bit here for the photon, okay, this is tiny. This is almost close to meaningless because it's so small, but it's not, right? Because, a light bulb is giving out, a ridiculous amount of photons each second. So, this evening, just spend, 10 minutes looking up light sails. It's really, really interesting and could be a future of space travel where we actually shine light at something and use the momentum of light to propel a spacecraft into interstellar space. Okay, one more question, and then I'll stop speaking and set you a longer task. So pause the video now and give yourself a minute or two for this question. Part B, pause the video now and give yourself a minute or two for this question. And finally, part C, pause the video now and give yourself a minute or two for this question. Please mark your work. Pause the video now, give yourself a couple of minutes to mark your work. Okay, so what I'd like you to do for the rest of the lesson is to complete the Quantum Homework Pack 3. Now, I know it's a homework pack, but I think it works really well with this lesson. So it's a really good test that you've actually listened, understood, and paid attention. But I'm also, because I'm trying to make this as similar as possible to a normal lesson, also going to set your homework for next Monday, and that is going to be the second Quantum Homework Pack. And then as soon as I'm back in school, I'll collect this week's homework off you and obviously next week's homework off you. You can find both of these booklets in the black cupboard next to the teacher's desk. They should be on the second shelf down. I think they're on the far right-hand corner. The cardboard box is ripped slightly. I think there might be a couple of random homeworks on top, but it's somewhere in that box there will be these homework packs. If you have any burning questions that you don't understand or you want to ask me about anything, feel free to email me. I will try my best to respond up until about 5 o'clock when I'll stop work. And hopefully I'll be back in school by Wednesday. So if you need anything, I can help you out then. All right. Thanks, and enjoy the rest of the lesson.